Welcome to the method of continuous variation. So let's suppose that P and X form several complexes. We can get P plus X to give us Px, we can get P plus 2X to give us Px2, P plus 3X to give us Px3, and so on. Now suppose that one complex predominates, as it will, since the formation constant values, the Kf values, won't be equal. But suppose that we don't know which one will predominate. We can identify the predominant complex using the method of continuous variation, or Job's method. We mix P and X and dilute to constant volume, and in doing so we keep our total concentration constant. That is, the concentration of P plus X, that sum of concentrations, is a constant. For example, on the next slide, we have over here the number of milliliters of 2.50 millimolar of P. We have here the number of milliliters of 2.50 millimolar of X. Here we have the mole ratio, and here we have the mole fraction of X. So we measure the absorbance of each solution, usually at lambda max for the complex, and we then make a graph of corrected absorbance versus mole fraction of X. So here we have the mole fraction of X on the bottom. We have our corrected absorbance on the left side there, and you can see we've got some curve where each one of these points here represents the absorbance at some wavelength. Again, it's usually going to be the maximum absorbance wavelength for our complex. So the maximum absorbance here at this point is at the composition corresponding to a stoichiometric mixture of our predominant complex. So in this case, our ratio there is around 0.33, so that's a mole fraction of 1/3. The corrected absorbance is the measured absorbance minus the absorbance of our free P and free X. So the corrected absorbance is the measured absorbance minus the molar absorptivity of P times the path length times Pt minus the molar absorptivity of X times path length times Xt, where again here epsilon P is the molar absorptivity of P, epsilon X is the molar absorptivity of X, B is our path length, Pt now is our total concentration of P in solution, and Xt is the total concentration of X in solution. Naturally, if the molar absorptivity of either P or X at the wavelength of interest is 0, then this correction is unnecessary. That is, if they aren't absorbing at that wavelength, then we don't need to bother with correcting for their absorbance. The mole fraction of X at maximum absorbance is the mole fraction of X in the predominant complex. Note that the mole fraction of X in PaXB then is the mole fraction chi X, mole fraction of X, is equal to B over B plus A. And let's look at the table on the next slide. If we have the formula Px, then the mole fraction of X is 0.5. If we have Px2, then the mole fraction of X is 0.667. If we have P2X, then the mole fraction of X is 0.3. If we have Px3, then the mole fraction of X is 0.75. P3X, the mole fraction is 0.25. P2X3, the mole fraction is 0.6, and so on. So for our earlier graph, where we had a mole fraction of X of 1/3, that's this point. So our complex has the form P2X. So you should follow these precautions when using the method of continuous variation. You should check that the complex follows Beer's law. You should keep ionic strength and pH constant if those are applicable. You should record absorbance measurements for multiple wavelengths. They should all reach the maximum at the same mole fraction. You should repeat the procedure for a few different total concentrations of P plus X. The maximum should still occur at the same mole fraction, as they do here. Now, we could perform the method of continuous variation using many different solutions prepared as in the table above. But it's probably easier to simply perform a titration. That was the method of continuous variation.